All right. So, hello and welcome everyone to week 10 of the course on fundamentals of convective heat transfer. It's being offered by NPTEL. The course is being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD student at IIT Madras, and like every other week, we shall be solving some problems together. So, this is week 10. We are, nearing towards the end of this course. Only 2 more weeks left, and I guess as far as lectures are concerned, lectures up to week 11 has already been uploaded. So we have completed our discussions on natural convection the previous week, and week 10 was all about how to numerically solve for problems of convection of any kind. Now that involved solving for the fluid mechanics of the problem, which required us the continuity equation and the conservation equations of momentum, which are essentially known as the Navier-Stokes equations. And on top of that, since we are dealing with heat transfer here, we have to solve for the energy conservation equation as well, which is sort of a transport equation for the thermal energy contained by the fluid. So in simple cases where those equations can be solved, they can be solved analytically, things are fine. But when the geometry becomes complicated, or even when the geometry is simple but all the terms in the equations remain, even in that situation, all the partial differential equations cannot be solved simultaneously. So in those cases, we need the help of numerical tools to break those partial differential equations down to algebraic equations so that they can be solved using a computer, a digital computer. And as we know that with the evolution of much better processors, we are relying on numerical techniques more and more these days, whether in industry or in academia. So without any further ado, we will jump into the questions of today. So here we have question number 1 of today's session, which is a match the following type of a question. It's asking us to, so on the left column, we have option A, equilibrium problems, and option B, marching problems. And on the right column, we have different kinds of PDEs, uh, categorized by their numerical classification, whether uh, it's a parabolic PD or a hyperbolic PD or an elliptic PD. And PDE over here means partial differential equations. So you have to match the options given in the left column with those in the right column. And once you have figured out the correct combination, you can select the correct solution from the options given here. So we have 4 options here. Option A saying it's uh, A matching with 1 and B with 2. Option B saying it's A2, B3. Option C is telling us that it should be A3 and B both 1 and 2. Or option D, which is telling us A should be matched with both 1 and 2 and B should be matched with 3. So there's no hurry, take your time, and once you've figured out the solution, you can either unmute and answer or you can type it in the chat box as well. So from the nature of the problem, you can see that it's not a one-on-one mapping between all the items of the two lists, since there are unequal number of items in both. There is 2 in one and 3 in the other. So it could be 1-on-1, or it could be 1 and 2, or 1 to 3 as well. Anyway, that is not included in the options, but that's a possibility. We have a quick response in the chat box saying that it should be option A, that is A1 and B2. Let's see what others have to say. Another response in favor of option C. Okay, good. Let's see if we can get any more responses. Option C again. Okay, good. So let's have a look at the solution. The solution is actually option C. So both of you are correct. Well done. So A should be matched with 3. That is, an elliptic PD is the uh, is an equilibrium problem, and both parabolic PDs and hyperbolic PDs are marching problems. So what happens is these two types of equations are usually they have a transient term and some space derivative terms on the other side. So it could be first order derivatives, it could be second order derivatives as well. Anyway, blah blah blah. So in this case, what is done is that you can solve it in an explicit manner in which whatever is your uh, variable that you're solving for, you can take it at the n plus 1th time instant, and everything else you keep them at the nth time instant. So the nth time instant is the solution that you already have, and n plus 1th is the next one. So basically, you can go on marching in time and finding out the solutions at the next time instant, then at the next time instant. In this subsequent manner, you can go ahead. So both parabolic partial differential equations as well as hyperbolic partial differential equations can be solved in this manner. That's why those are called marching problems. And that's not only limited to time derivatives. As we know, in a boundary layer, the equations of a boundary layer are also they also qualify as parabolic PDs, and in that case also you can go march, but not in time but in space. So the streamwise direction in the boundary layer flow uh, acts essentially in a similar way like time does in other parabolic equations. So anyway, that doesn't matter here. And elliptic PDs, they are basically boundary value problems, and usually they are for stable systems where you have one good example is the Laplace equation. So dou x square of phi plus dou square phi dou y square equal to 0. This sort of a thing where you have accompanied with that are some boundary conditions as well. So in that case, you find out what the solution is within the domain at the steady state, and that steady state is also an equilibrium solution. It does not evolve with time or space or anything. So elliptic PDs, that's why, are known as equilibrium problems, because you find out the equilibrium solution, the equilibrium state of that system. Okay, so that's why option A should match with 3 and option B should match with both 1 and 2. And subsequently option C should be the correct solution. Any questions on this? Okay, if not, we will keep moving on. We'll move on to question number 2, which is again a simple question asking us that numerical schemes used for solving convective heat transfer are what? So there are 4 options given below. Option A, finite difference method. Option B, finite element method. Option C, finite volume method. Or option D, all of the above. So the question is basically asking us that for solving convective heat transfer, what kind of numerical schemes are usually used? Is it option A, finite difference, option B, finite element, option C, finite volume, or option D, all of the above? Okay, we have one response saying that it should be option A, finite difference method. Where is this vanishing away? Okay, so in the chat box we have two responses in favor of option A. Let's see what others have to say. So let's have a look at the solution. The solution is actually all of the above. It's not only finite difference method, but finite element method as well as finite volume methods are other numerical ways to discretize the partial differential equations to algebraic equations. These are different philosophies. We have learned finite difference techniques in the lectures that we have covered, but there are other methods also to discretize the governing equations of convective heat transfer. So that's why it should be all of the above. Both A, not both, all A, B, and C are different numerical schemes uh, which are used for solving problems involving convective heat transfer. Okay. Any questions on this? Okay, so it was a simple one. We will keep rolling. We'll move on to question number 3, which is now asking us that order of accuracy of forward difference discretization scheme is what? Is it option A 1, option B 2, or option C insufficient information? That is, the information given in the question is not sufficient to determine the order of accuracy. We have one quick response telling that it should be option C, insufficient information. Forward difference discretization scheme. What is the order of accuracy of that? Is it option A 1, option B 2, or option C insufficient information? No more responses. Any guesses? Okay, someone says it should be option B, that is 2. Anyone else? Any more guesses? Okay, so let's have a look at the solution. Yeah, So the correct solution indeed is option C, insufficient information. So one of you responded correctly. Well done. But why is it so? What is the information that should make this sufficient? What other information do you need to know? Or which is the information that is missing over here? Hmm? You can unmute and answer, or you can type in the chat box as well, any way you feel comfortable. So one more piece of information missing here is the number of points considered. So in a simple way, let's say if I took only 2 points, I and I plus 1, which is usually done. So in that case, let's say if f is the function that I'm looking for, then the first derivative dou f dou x should be fi plus 1 minus fi divided by delta x. And this thing is actually first order accurate. We can find out the order of accuracy by expanding fi plus 1 in its Taylor series and then find out the order of the highest term that is being truncated over here. So if we use only 2 points in forward difference, we will get an order of accuracy of delta x only. If we use central difference, then we might have gotten a second order accurate solution. But I can get a higher order of accuracy out of using 3 points only. So let's say, let me try to work this out. So fi plus 2 can be written as fi plus 2 delta x dou f dou x plus 4 delta x squared by 2 factorial into 2 df2 square plus dot 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 plus higher order terms. Then fi plus 1 can be written as fi plus delta x into dou f dou x plus delta x square by 2 factorial into dou 2f dou x2 plus dot dot dot. Let this be equation 1 and this be equation 2. Then if I try to eliminate this, so I'll take equation 1 minus 4 into equation 2. So what will I get? Fi plus 2 minus 4 fi plus 1 this side. Then I'll have minus 3 fi over here, and then this would be 2 minus 4, so minus 2. Minus 2 delta x into dou f dou x plus this second order term would vanish. We are eliminating this, and there will be some third order terms over here. So there will be some truncated terms, but they would be a third order. So now if I simplify this, so then I'll get, so I'm trying to solve for this. So it would be dou f dou x. I'm taking it this side. Then over here it would be 4f. Let's not start with this. So it would be 3fi plus 4 fi plus 1 minus fi plus 2 and divided by 2 delta x. And remember, this term would again get divided by delta x, so I'll get order of delta x squared now. So using 3 points and forward difference scheme, I could get a derivative which is second order accurate. So I could use 2 points and get first order accurate. So it could be option A, could be option B, depending on the number of points used. I can use even more number of points to get even more uh, order of accuracy, right? So in the absence of that information, you cannot really say what is the order of accuracy of any forward difference scheme. So number of points is the insufficient or the missing information here. Am I making sense? Any questions on this? All right. So if there are no questions, we will move on. Okay. What happened here? Okay, this slide seems to be problematic anyway. So we already have the solution slide here. So we will go through this quickly. What are the this question is asking explicit schemes are what? Are they unconditionally stable, unconditionally unstable, or conditionally stable? So as you can already see from here, the explicit schemes are conditionally stable. Why is that? So uh, implicit schemes, on the other hand, they are unconditionally stable, and on the other hand, explicit schemes, they are conditionally stable. Some of them. Some of them are even unconditionally unstable, that is, they'll never be stable. So a more detailed discussion of this can be found in any CFD course. So as of now, all you need to know is that for explicit schemes, the uh, time discretization or the time step that you're taking, that should be less than some other time scale associated with the problem. There is something known as a CFL criterion which governs this, which governs the value of this uh, you know minimum time step that should be taken, or the maximum time step that should be taken. You can go below that, but you cannot go above that. And this is usually this is around u delta x over x divided by u. Yeah, so it should be around delta x by u, which is the time scale associated with the problem. Any questions on this? Sorry about this one. That slide somehow didn't turn out well in the PDF. Okay, we will keep moving on. We'll move on to question number 5 now, which is asking us that implicit schemes are solved by what? Option A, Kramer's rule. Option B, Gauss elimination. Option C, Jacobi method. Option D, Gauss-Seidel method. Or option E, all of this, all of these. Implicit schemes. Focus on this. So how are implicit schemes solved? Okay, we have one response telling that it should be option E, all of these. Okay, another response in favor of option E. So let's see if everyone disagrees with you. It says that it's not all of these, but only one that is actually used to solve implicit schemes. Okay, so let's have a look at the solution. The solution is indeed option E, all of these. That is, all these four methods can be used for solving implicit schemes. But however, in practice, it's this Gauss-Seidel method that is used because these three things, Kramer's rule, Gauss elimination, and Jacobi method, these are direct methods, and direct methods are very much computationally expensive. So that's why methods like Gauss-Seidel method, which does not involve solving the inverse of a matrix. So it's usually something like this. It's matrix A multiplied by vector B or vector X, giving us uh, another vector B, and we're trying to solve for X by taking the inverse of matrix A and multiplying it with vector B. But solving this inverse of a matrix numerically, if you simply try to do it, you'll understand that it involves a lot of steps, and this is computationally very expensive. So in a case where a big CFD simulation is running, where you have to find out the inverse of these matrices at every step, that doesn't really make sense to do it using these direct methods. It's much more simpler to use an indirect method which does not involve solving for the inverse of a matrix. Rather, there are other ways to approximate this value of this x vector, the physical quantity that we are uh, trying to solve for. Okay. Any questions on this? Okay, so we will keep moving on. We'll move on to question number 6 now. So this is asking, so for MAC algorithm, different steps are given, which are followed for solving a problem using MAC algorithm. But these steps, they are jumbled up. They are not in proper sequence. It's not that if I go from following step A to B, C, D, E, F, that I'll be doing, that I'll be performing MAC algorithm correctly. What you have to do is you have to find out the correct sequence of these steps, and once you have figured out that, you can match with the options given here. So we have 4 possibilities given here. uh, there could be multiple ones, so there are 6 steps here, so it could be uh, a total of 6 factorial ways in which you can arrange this, but you have to pick out the correct one, and there are only a few steps that are given here. So either it's option A, step A, B, C, D, E, F, telling that this order is perfectly correct, or option B, A, C, F, E, then D and B. Option C telling that it should be A, F, C, D, E, B, or option D, A, C, E, F, D, B. Trying to figure out these sequences and then matching might not be the smarter way of doing things. Instead, you can make one observation that option A is the first step in all these cases. From there, you try to just find out what step makes sense next, and then find out the the sequence of steps that should be followed, and it should, if you're doing that correctly, it should match with one of the options given here. Okay, there's no hurry, take your time, figure out the correct solution of this. Okay, we have one response telling that it should be option D already. Okay, pretty quick. Let's see what others have to say. Step A is initialize u, v, w, p, and t. That is all the vector and scalar values that we will be solving for. Step B says check for convergence, repeat if necessary. Step C says predict provisional velocities. Step D says solve for the scalars, for example t, or p as well. Anyway, if there is concentration difference or binary mixtures, then mass fraction would also come in over here. Then step E is update velocities, and step F is find pressure correction. Okay, we have another response telling that it should be option B. Let's see if anyone else has any other answer. Okay, let's have a look at the solution. Solution is indeed option B, so you're right. And let's see, so what are the steps that are usually followed? The step 1 is always initialization, right? So there is step A. Then in step B, we find out the provisional velocities, that is u tilde, v tilde, w tilde, using the pressure at the nth time level. right? So this is predict provisional velocity, so step C. Then in the third step, what we do is we put in this, we use the values of these provisional velocities to find out the pressure corrections. So the P dash terms, P dash N, that is step F. And after we have calculated the pressure correction terms, then comes the step to update the velocity. So using these corrected pressure, so Pn plus 1 should be equal to Pn plus Pn prime, that is the correction term. And using these, we find out the velocities u, v, w at n plus 1th time level. So this is the step update velocity, that is step E. Then for the next step, I'm going here. So the fifth step, after you have calculated the velocities, then is when you solve for the vectors. The pressure P is already solved. Any other scalars like temperature, mass fraction, and so on, those scalars should be found out at this step when we have the velocity field with us. So let's say in this case, like we have the energy conservation equation would be solved at this step to find out T, right? So this step is step D. And for the last step, we will check for convergence and repeat if necessary. So this is step B. So what should be the correct sequence? A, C, E, sorry, A, C, then F. A, C, F, then E, then D, then B. A, C, F, E, D, B. That is option B. So that's why this is correct. Any questions on this? Sorry. Okay, so if there are no questions, we will move on to the next question, which is a simple one. Question number 7 is asking us the problems of using collocated grid are what? Is it option A, checkerboard pattern, option B, pressure velocity decoupling, option C, both A and B, or option D, none of the above? So what are the problems of using a collocated grid? Is it option A, checkerboard pattern, option B, pressure velocity decoupling, option C, both A and B, or option D, none of the above? We have one response telling that it should be option C, both A and B. One more response in favor of option C. Okay, so everyone agrees that it should be C. Let's have a look at the solution. It is indeed C. So we have seen in the lectures that if anyhow a checkerboard pattern occurs in velocity or pressure, then it would affect the solution of the other one. So if velocity obtains a checkerboard pattern, let's say 1, 2, 1, 2 like this, then the pressure field cannot be solved correctly, and this goes the other way as well. So if pressure obtains such a checkerboard pattern, then velocity would give an incorrect solution. And if we use a collocated grid, the pressure velocity coupling is also very weak. So at any location, so let's say at this location, the pressure over here is 1, the pressure over here is 1. So if I try to find out dou P dou x using a central difference scheme, I would essentially get 1 by 1 minus 1 divided by 2 delta x, giving essentially 0. But in reality, the pressure gradient does not vanish over here. There is a strong gradient there, but dou P dou x is coming out to be 0, and that would give rise to wrong solutions of velocity as well. And this goes the other way as well. So uh, the gradients of velocity vanishing in this way would mean uh, an incorrect solution of the pressure fields as well. So this is known as pressure velocity decoupling. There are ways to remedy this. There is a one remedy known as momentum interpolation technique. But anyway, the scheme itself of using a collocated grid leads to very weak pressure velocity coupling. That's why staggered grids are used more frequently. So these are the two problems of using a collocated grid, and that's why a staggered grid is preferred. Okay, is everything clear? Any question? Anyone? Okay, if not, we'll move on. We'll move on to question 8, which is asking us what are the different upwind schemes. Is it option A, first order upwind, option B, second order upwind, option C, quick scheme, or option D, all of these? Okay, so two of you are telling that it should be all of these, option B. Maybe B. Okay, we'll take a maybe and then have a look at the solution. And indeed, it is option D, all of these. So first order upwind scheme uses simply one point upstream to the point. So if U is positive, then the upwind point of point I is I minus 1, and if in case U is negative, that is going from the right towards the left, then the point upwind of I is actually I plus 1. So depending on the direction of velocity, these upwind points are selected. And similarly, there is a second order upwind scheme as well, in which another point is included to make it second order accurate. And quick scheme, the quick is actually an abbreviation of, let's see if I remember this correctly, it's quadratic upstream interpolation for convective kinetics. So if I take the first letter of each of these, I will get quick. So this is also a third order accurate scheme using, I guess, 3 or 4 points, 4 points actually, to and this is third order. So the order of accuracy is 3. And so the problem with first order upwind or second order upwind is that we get a artificial diffusion, which is not a physical phenomena, but rather it's a numerical artifact that comes in. So to combat this, quick scheme was developed, which did not have the problem of artificial diffusion. So to answer this question, what are the different upwind schemes? All 3 of these are upwind schemes, and that's why option D, all of these should be the correct answer. Any questions related to this? No? Okay, so we will move on. Okay, there are no more questions today, so that's all for this week. Thank you guys. Thank you for participating. We will meet again next week. Thank you.
Sir,
Yeah.
sir, they keep updating the detailed solution of different. It's not supposed to be in that. That means they are updating different answers, sir. That are different from the questions they given for the assignment. Can you please tell them to
Okay.
update?
I actually told them for the first 2 or 3 assignments I had mentioned. Have they corrected that yet? I
The
don't think they have, right?
old one, I think, sir.
Old one
They
they
keep
have
up.
updated.
Uh, yes, sir. That's
Okay.
not that's not matching with the questions given for the assignment, sir.
So the detailed solution that is uploaded, that is wrong, right?
Yes, sir. Yes, sir.
Okay. I've let them know, but I don't know.
Okay, sir.
It's not
Okay,
really
sir.
in my hands. Sorry. I've let the
Okay, sir.
NPTEL team know, and maybe I can give them another. I can communicate with them once again as well. Okay.
Okay, sir. Thank you, sir.
Hmm. So if you have any doubts regarding any of the assignment problems, you can ask them here as well, since you are not getting the correct solution. Okay.
No, sir, but it will be helpful. No, sir. At the end of the
Yeah,
day,
of course, you should get it there. But if you do not, if the problem remains, then you can come here. That's all I'm saying.
yeah, sure.
I can't update the detailed solution there, but we can
Okay,
discuss
sir.
it over here in this class. That's what is in
Yeah,
my
sure.
hand. Okay.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Thank you. Good night.
Good night, sir.
Yeah. See you again next week. Bye.
Thank you, sir.
Thank you.